Hi everyone, this is Dr. Data Science Office Hours. Today it would be Stephen Hillen and Prem Shah that would be covering today's Office Hours session. And today we would be talking about Dr. Data Science sessions, and Dr. Data Science is offered every third Wednesday at 9 a.m. Pacific, and the next session for the next month is on October 21st. And the session recording is in the YouTube, and I will post the link in the YouTube channel here. And please post your questions using the question and answer section of Zoom, and I would be using the chat to post the information about this session and other information links. I would be passing on to the presenters, Stephen Hillen here. Stephen, here you go.
Thanks, Nilima, and welcome everybody to this September session of Dr. Data Science. Got a couple of interesting topics to talk about. You remember last time, if you were with us, we talked a little bit about how to explore new data sets. As usual, we kick off our sessions with sort of information gain, as we call it, a quick topic of general interest, sort of general technique that we think is useful. And then we have our featured session last month. It was looking at different methods for categorical encoding. We had one of our interns from this summer at TIBCO give an overview of which methods work best for encoding different types of variables. You can always check out, as Nilima mentioned, previous sessions on YouTube. So if you just go to YouTube and search for TIBCO Dr. Data Science, you'll see there a channel of all of our presentations. I think there's quite a few of those now, and there's some really fun topics there for you to review. So I encourage everybody to take a look. This month, we're gonna have, as usual, a quick info gain session at the beginning. We're gonna talk about correlations and relationships between variables. And then we're gonna dive into a review of how to explain models. We're gonna look at a topic that I think these days is gaining more interest, how to interpret your models. I think it's gaining interest for a couple of reasons, because models are becoming more opaque and governments are getting more curious. So that's a topic that we're going to be discussing with Prem. Okay, so let's get started with the info gain. And as I said, this is going to be about how two variables are related. This is really going to be a bit of a teaser for an upcoming session. I'll talk about that in a second. So if you've got two variables in a data set and you want to find out how they're related, what are the methods that we can use to do that? So let's switch to the next slide now, where we talk through a few of these methods. There's some basic rules of thumb that I tend to use. And of course, everybody has their own techniques and tricks for looking at relationships between columns in a data set, between variables in a data set. But these are the ones I typically go through. The very first thing I do is to try and plot one variable against the other. That's easier, I guess, if both of the variables are numeric. You can do some sort of scatter plot, and you can see if there's maybe a linear relationship between them or something more complicated, or if it's just sort of a random set of points. Even if you have categorical variables, you can do things like sort of heat maps for understanding where the most common intersection of those categorical variables is, or you can maybe do frequency charts or bar charts that show how a numerical variable varies according to the different categorical variables. If it's ordinal, categorical but ordinal, you know, there are again variations there. You can use scatter plots and various other charts. So using plots will help you when using a sample from the data to understand how those relationships look sort of visibly. But there are mathematical tests you can use. If both variables are numerical, I think the standard thing to do is to use sort of Pearson's coefficient, which will look for linear relationships. So there may well, of course, be very strong relationships between them, maybe some sort of quadratic relationship that would not show up at all as interesting from the Pearson's coefficient. So do be aware that it's just for linear. If they're not linear but still ordinal, there's some sort of monotonic relationship between one numerical variable and the other. So something like, you know, sort of salary and educational achievement, something like that. If you have ordinal variables like that, then the Spearman coefficient, Spearman index can give you an indication of how strongly those are related. Spearman sort of just looks at sort of the rank of the variables as you compare one to the other. So those are sort of the standard methods, I think, for numerical. If both variables are categorical, then I think the typical method to use is this chi-squared test, which looks for not correlation, obviously that's sort of a specific term for numerical variables, but is there some sort of relationship? Are the two variables independent of each other? I guess it's easier to state the null hypothesis, and chi-squared will tell you whether that's likely to be true or not. If you've got one variable that's numeric and one variable that's categorical, then, well, you know, in the sense there, you're doing something like a logistic regression, or you can use ANOVA to see how the numerical variable affects the categorical variable. So I think those are sort of standard techniques to use there. But as I was putting this list together, I realized, well, you know, things are actually a little bit more complicated. First of all, when I was just sort of Googling around for this, I found that other people do things that are just completely different, use different coefficients apart from Pearson and Spearman. There's a number of other ones out there that people find useful. For categorical variables, it's a lot less cut and dried what you should do. And then, of course, there's like time series variables. So if both of your variables are actually sequential, they both have an additional dimension in them, then there's all sorts of interesting tests that you can apply there. There's a method called matrix profiling. There's one of the coolest names I've ever come across in terms of statistical techniques, which is dynamic time warping. The point here is that this is actually a more complicated subject than I'd originally anticipated when I was putting this checklist together. I think there are sort of tried and true things to do, which I've tried to list out here. But I was chatting with one of our data scientists, David Katz, and he was saying, wow, there's just a whole host of things we can talk about. So this is, as I said, a little bit of a teaser for a session that we're going to have, I think in November. We'll be having that. So David Katz, one of the illustrious data scientists on the TIBCO team, will be joining us to talk about, in general, how do you compare variables one against the other. If you want to cheat, by the way, you can use Spotfire, TIBCO's own exploration and visualization application. So within a Spotfire dashboard, well, within the Spotfire application, rather, you can go to the data relationships item in the menus, and that will automatically apply various tests and statistics to your data set in order to find those relationships. So it'll actually use some of the ones that I've mentioned here today. I think it uses Pearson, for example. I think it has chi-squared built in there as well. You can also do sort of logistic and linear regressions to find relationships. Very handy, very convenient. You don't have to write any code. So if you're a Spotfire user, and why aren't you, then go and check that out. Okay, so that's my just brief overview. Let's go on to our featured session now with Prem. Prem, thanks for joining us today. How are you doing?
Of course, I'm good. How are you, Steven?
Great, great, really good. So you had suggested this topic actually, and I was amazed that we hadn't done this before. It's such an obvious and pretty fundamental thing that a data scientist has to do when she or he is creating predictive models, which is to try and explain them. But maybe, Prem, you could give us a little bit more of an in-depth review of that. Why do we want to explain models in the first place?
Sure. Okay. Thanks, Steven. Why explain models? That's a good question. I think what we're looking for is mainly three different things. Models inherently are supposed to be black boxes unless you make an effort to kind of uncover what's going on inside them. Mm-hmm. And why do we want to do that is because you want to know what's going on inside, because you want to know how it can help you understand your data better, understand your decisions better, understand your business itself better. You also want to do that because you want to make sure that you're using the correct model, you're using it in the right way, and you're using it in the right environment. By environment, I mean that, if you're doing a classification problem, you should know when to use a simpler model in comparison to a complex model. When the trade-off is between you want to understand what's going on in the model versus you want to have more accuracy, and just actually build a complex model.
I
You
know
also
for
want
me,
to
Prem,
do,
on that, sorry, just to interrupt you. I know for me on
yeah, no
that
problem.
second one around correctness, like just if you do have visibility in the model, like sort of, you know, in a simple regression, right? I don't mean simple, in a basic regression where you're just using like a linear or logistic regression, just looking at the coefficients to see if they make sense is something I always do, right? Because if you're looking at sales versus price and there's a positive coefficient there, that's probably a sign that something's gone wrong with your model.
That is true. That is correct, Stephen. So that's what Stephen gave as an example of a fairly interpretable model, where you can at least understand what kind of coefficients are attached to your own data variables, and you can uncover relationships in between them. And the third reason we want to do model explainability is because of model safety. Just to understand if there's an inherent bias in the model because of, you know, the way you're using your model or the way your data is being structured. There might be a reason that, you know, your data is being skewed heavily towards one category or one you know, subclass, and you do not want to do that. And you want to make sure that the model is fair to all classes. And that is one more reason to actually use model explainability in order to understand, you know, if you're doing anything wrong in terms of putting the wrong data in or using the wrong model.
I guess this is increasingly important these days, right? We've got more and more regulation around this. I mean, there's the obvious case of GDPR in Europe, if I have that acronym right, which is, you know, insisting that basically at a high level, we can explain what we're doing, explain how we're using the data, and that we're doing it in a fair way that doesn't affect one particular group in an unintended sense that might introduce bias in the offers we make in terms of products or the loans that we make from a bank. So yeah, I agree. That's a big one.
Of course, that's a big reason, and also because of the unfortunate, you know, reason that the pandemic is here. A lot of the buying patterns and kind of customer patterns have been changing a lot, which is kind of influencing, you know, your data to change and skew a lot, which is one more reason to actually use model explainability to understand what's going on in your model.
Yeah, good point.
So coming on to like model itself, there's a couple of examples of models where they are pretty much self-explanatory. And in terms of, you know, you don't have to use explicit methods to actually explain what's going on inside. Some of them are like pretty standard, like decision trees. The name itself speaks for the model, is that, you know, you are constructing a decision tree based on some decision that you make from the root to the node, and what it helps is it kind of gives you an answer to, you know, what is the most important variable in building the decision tree, what's the second most important one, things like that. Even standard regressions, as Stephen mentioned, help you understand what kind of coefficients and the strength of the coefficients are there for each variable, which helps you in a particular way, helps you understand if there's, you know, strong relationships or statistically significant relationships between your variables and the outcome itself.
Yeah, one reason that again, sorry to interrupt, Prem, but I find this stuff so interesting. I mean, we actually just added a new, we have this notion of Spotfire mods, right, where we can add new visualizations to Spotfire. And one of our interns is actually working on adding a decision tree, not so much for predictive modeling, but actually to help explain the contents of a data set. So you actually use a decision tree to say how one variable depends on the others. So decision trees can actually be used as a mechanism for explaining data. So I think it's a good example. And I think one of the reasons why like regressions, especially logistic regression, remains so popular despite all these sort of new fancy trendy models is because it's so clear in your head what it's doing, right? It's just taking variables, multiplying them by a weight, and then essentially giving you the answer back. So yeah, they're very self-explanatory. What do you mean there by ensembles, sort of?
Yeah, but sort of ensembles is the sort of is like an asterisk, if you can put it.
Right.
Is you know, ensemble models basically mean when you're combining different models to get better results. And so in some cases, ensemble models can give you some idea, like let's say a random forest, or, you know, XGBoost modeling can give you some idea and some insight into what kind of overall globally variables are important, but might not be able to give you an exact idea of, you know, why is this row being classified as yes, or why is this row being classified as a no. for example.
Yeah.
So ensemble modeling can be advantageous in terms of getting you better results in some cases, but might not be advantageous in terms of getting you like really down to the
You
weeds.
can't see the forest for the trees, so to speak.
Yes, exactly. That is a correct analogy. And some counterexamples where it's really difficult to understand what's going on, and it's basically where the term black box models came from, is neural networks and SVMs. SVMs are really hard to understand because they define different kinds of decision boundaries, and neural networks because they have different number of hidden layers. If you want to do deep networks, if you want to do simple networks, even then, it's hard to uncover because all they work on is backpropagation and basically understanding the data itself without actually applying any kind of decision-making process that we can understand, like a decision tree.
Got it. Yeah, so I'm really interested to see what you have to say about just generally when you do have these more black box models, what methods can you use to sort of peer into them and see what's going on?
Of course. Yeah. So today I'll take you through an example that we, as a personal project did at TIBCO with a couple of my colleagues, where we defined a problem statement that we all were concerned about, and we wanted to see if we can come up with a solution for the problem statement in whatever way possible. And so what we kind of wanted to address was, we at TIBCO have been looking at COVID-19 insights a lot. As some of you might know, we have a public COVID dashboard that
right.
looks, scientifically into how the COVID-19 is progressing in different states and countries across the world. And so what we also knew was that a lot of the pandemic's effects were, kind of forced onto data itself. As a consumer, I can know that my buying patterns have changed over the last 6 months, heavily towards e-commerce, less towards in-store shopping. Then that's just one example of how data can get skewed in today's times, especially during the pandemic. And so what we wanted to understand is, are there any biases or driving factors that stand out because of this kind of shift? And we wanted to, take a data set and explore the socioeconomic, ethical, and potential sources of bias as applicable to that industry. And many models unfairly biased by gender, age, ethnicity, just because the data itself is skewed inside the model that comes inside the model. And so we want to make sure that we understand that that is something that's going on in our model so that we can correct the data itself, or we can use some different kind of data. For example, COVID, it's well known that it has impacted ethnic young minorities the hardest because of the data has generally been skewed against them, against their favor, and it's become more and more prominent during COVID times. And so it's become more important than ever to understand and detect bias and basically driving factors that drive your model itself in different industries. So we came up with an example where we had a credit loan data set. And what we did was we built a workflow in Team Studio, and we applied the general data modeling techniques, data cleaning, preparation, data engineering, and then model building, and then model evaluation.
Is sort of a visual workflow, correct?
Yes, that is a completely visual workflow without no code involved at all. On the top left, you see the data science workflow itself. What we did was we extracted the XML out of that workflow that is easily available from the TIBCO data science product. We analyzed it and converted it into structured tables, and we decomposed them into structured tables for each operator inside the workflow. So what we had was details inside what kind of variables is each operator using, what kind of conditions are applied to each operator, things like that. And so the reason for doing that,
meta-analysis, so an analysis
yes,
of their own analysis. I got it. Yeah.
Exactly. So like basically a metadata analysis on the data science workflow itself. Basically, the reason for doing that was to understand what's going on at each part so that we can uncover problems if there are any on each section itself. And so after we did the decomposition, we brought the data into Spotfire to understand what kind of things are going on inside. And I'll take you through those right now. So the first page you come to is this really nice Spotfire dashboard where you see that these are all the operators that are used. So first we use a text file itself as the input. Then we use a confidence threshold, a null value replacement after that. We remove dependent variable nulls, things like that. So all of these are different operators inside TIBCO data science that we are using. And we gave them different categories according to what category they lied under. Was that is it data gathering, is it data prep, feature engineering, model building, and model assessment. And so what we were trying to do is kind of highlight what kind of issues that can happen with each. And so we kind of color coded them according to, basic colors. Is if it's green, then it's probably fine. If it's red, then there's definitely an issue with it. And warnings were highlighted with yellow. So
can you give us an example?
Sure. Yeah. So you can see that there's red on converted interest rate to numeric. And if you hover over that particular operator in Spotfire, you'll see that it's expanded right here, and see that there's some reasons given why it's red. So you see that there's null values and too many categories, which might pose a potential problem for the model to understand and the importance of this particular variable itself, that is interest rate. And so this way, if you hover over each one, you can see what kind of problems are there, if there are any, or any warnings. And so the reason for doing this was to, at a very high level, understand what the workflow has done for each operator. You can also see a network graph of each of the operators that are being used in the workflow, and you can see that they're color coded the same way. If it's red, then it's a potential issue, and if it's green, then it's fine. Warnings are highlighted in yellow, and you have a summary statistics, health check summary basically up here that can show you that in each stage of the modeling workflow, what kind of issues were detected or what kind of warnings were detected. So we can see that there's 3 warnings in model building and 1 issue in model building, which kind of gives you an overall idea of how that block is doing. And so once you remove all the issues, these will eventually go green, and you'll see a completely green page right here, which can give you an idea, easily give you an idea of, yes, you are good to move ahead.
Right.
One more analysis that we did was correlation testing. So as Stephen defined correlation, you can use Spearman for correlation, or Pearson's rank matrix for correlation as well. And there's some other different methods for categorical and time series variables as well that can help you define the relationships between the 2 variables. So what we did here was basically take try to take into account correlation that can occur between 2 input variables. And so if there's a really high correlation, by a really high correlation, I mean greater than 96, 97% between 2 variables that are going into the model, there's a chance that both of them give the model the same information. So using either one of them will be fine. Using both of them might be an issue. And so you can see here that all of the red ones have a correlation greater than 90% here. And all of those are input variables itself. And so what we try to do is highlight such variables that, that might not contribute to the model itself, but might pose an issue later as well. We also do, a warning kind of thing where it's within an acceptable limit, but it's still high correlation, be it, over the positive side or the negative side. You can also visualize the predictor's correlation across the target, and you can select different variables to do that. You also have a network chart of highly correlated columns and their interconnectivity, so you can easily see visually what's kind of going on between intercorrelated columns, and you can remove the ones that you don't want or you don't need in the model. You can also have response correlations with numerical variables. So here interest rate percentage is compared to age and loan approved. And if there's an issue with the response correlations, then it's highlighted here as well. Highly correlated columns can be an issue in models because multiple correlated columns can skew the model itself. And so it's better to use less highly correlated columns, intercorrelated, meaning that, multiple columns inside the input data itself are correlated within each other, which kind of creates an unfair bias on the model, which you don't want.
Got it.
Something else we did was we did a model prep workflow, is where basically understand how your model prep has been defined and how correct it is. So first of all, we look at training and testing, and if there's a response bias in that, we understand that as well. So what we did was we kind of plotted on a graph the distribution of the response variable in the training set and the testing set, and you can see that. You can see that the response variable in the testing data is skewed a little higher, than the one in the training data. That gives you a really good idea of that, you might need to change your split, or you might need to change the rows that are in each split so that you are using a very similar distribution across both the training data and testing data. This is important because you do not want your training data to not represent your actual population itself. You want it to represent as much as it can, of course, your actual population that's coming in. So it's important to make sure that your training data represents an overall correct population itself. You also can see on a bar chart the response bias. And you can see here that, it's relatively fine is that, so the loan approved or loan rejected are the two response variables. And the distribution across training data and testing data for the gender is fine. So that is something that you can also look at. You also look at, if there's more null values here, and you can look at the percentage of nulls in each category itself. And that kind of divided by the data science model used. So in TIBCO data science, you can use multiple models within one workflow. And so what we did was we divided the table by the data science model that's being used, and the issues and the alert level within each model. And
I think so you use some, Prem, sorry, just in the last few minutes, I think you use some open source methods, right, for sort of digging into the models further?
Yes, we also use some open source methods. I'll come on to that a little later.
Yeah, we've only got a couple of minutes left, but
oh, sure. Oh, okay. Yeah, so we also used for model forensics, we also used Lime and SHAP. These are two specific open source libraries for model explainability. So Lime means locally interpretable model agnostic explanations, which basically help you understand what's going on inside each row of the model. So in very high level, it kind of makes you understand, why is this row being classified as loan approved or loan rejected? And it gives you an idea of what factors are contributing to the loan being approved or the loan being rejected, and things like that. So each feature and its value is classified on a double-sided bar chart as to which way it's being targeted on. And traditionally,
so let me make sure I understand this. So it's saying we've made a prediction here, which is a positive event, the one event. And it's saying that different variables contributed to this in different ways. The two most significant contributions were from total payments they'd made and the amount of the loan. Those are the two most significant, and one of them affected it positively and one of them affected it negatively.
Yes, that is correct. And so this can give you an idea of, what kind of data you're looking at and what kind of things you should be careful about while, building a model itself. And it gives you a really good idea into why the model classified this particular row as loan being approved or loan being rejected. And so
you mentioned Lime is, this is in Spotfire, but this is an open source. How do I get my hands on this if I want to use it?
It's open source. It's on GitHub. You can use it within the data function capability in Spotfire. You can use it in the Python notebook itself, in TIBCO data science, or in an open source version as well.
Great.
And there's another similar library called SHAP, which uses game theory to help you understand the skewness of different variables in defining the outcome. It's a very similar method to Lime, but it's a little different in that it uses a different approach, but the outcome itself is similar. It gives you, so the model output value right now is 0.00, which means that the loan has been approved or rejected. And you can see that what it shows is which two variables have the most important effect on taking that model to that value. And you can see that this also corroborates our analysis with Lime, is that loan amount and total payment are the two most important variables itself in kind of defining the outcome itself. Shapley is also available open source in Python. It works in a very similar method to Lime, and as long as you use open source machine learning toolkits like scikit-learn or Keras, you can use Shapley and Lime pretty straightforward and easily with them.
That's great. Do you have a favorite out of those? I hear about Lime more than I hear about Shapley.
Lime's generally more well known, but Shapley's definitely up there as well. Still working on kind of deciding a favorite, but my go-to method till now has been Lime, but I just discovered Shapley a couple of months ago, so I'll be looking at Shapley more as well.
Right. Thanks, Prem. That's a good, quick overview there. And I think we have a few questions, right? Nilima, do you have any questions from the folks on the call?
Yes, thanks for the wonderful session. As we are almost running out of time, there are a few questions I will take from the audience. From a business perspective, how does model explainability factor into choosing a model?
So that answer would be kind of directed towards how you want your business or the outcome to be. Do you want the model to be more interpretable in terms of, do you want to understand what's going on inside more, or do you just want to build a really complex model to get, the highest accuracy and highest precision possible? What I mean by that is basically if your business outcome is dependent on taking into account what kind of data is coming in and what kind of data decisions are made, then you should use a more interpretable model. And if you just care about the result itself, you should use a more complex model.
Is there a sort of trade-off in a sense? Is it generally true that the more accurate the model is, the less interpretable it is? I wonder if there's some common sense there.
In some cases, it's generally true, is that, what happens is the more accurate you go, the more complex the models become, because they're trying to understand a lot more information. And as more complex the models become, it's difficult to understand and interpret what's going on inside the model itself. So if you keep the model simpler, you might not get the best accuracy out of all, but you will still be able to understand at a very good level what's going on and why is the model behaving like this.
Cool. Maybe one more question, Nilima. We can go over a little bit.
Sure. The last question, why bother digging deeper into a model? Why not we just run it and leave it alone?
So yeah, this kind of summarizes what, sure. This kind of summarizes what we've been what our problem statement was initially for, is that, interpretability understands factors that drive your model itself. And so it kind of helps you understand what's going on inside, and it helps you understand if there is, any potential presence of bias or skewness in your model that you would, as a data scientist, would ideally want to remove as soon as possible, because you don't want that model to go into production and then affect your customers or consumers. Might they be internal or external? And so the main reason for doing interpretability is in a fashion that you want to basically just clear out any issues or doubts that you would have regarding the model itself.
Thank you, Prem. Thank you, Steven. Thank you, everyone, for joining today. The next session on the Dr. Data Science of next month is on October 21st, and the topic is 5 charts to use in exploratory data analysis. Thank you for joining today. Have a good day and rest of the week. Thank you, everyone.
Thank you.
Thank you.